So up till now we have studied different characteristics of electrical characteristics of our MOSFET circuits, and we have also studied how to design them and how to design the layout of those circuits, and also we have studied about the fabrication processes which are involved in designing our CMOS circuits. From now on, for next couple of lectures, we will study about the advanced techniques in CMOS logic circuits. We have to study that how can we design our circuits other than the conventional techniques where we have been using the pull-up and pull-down network, where we designed the inverted logic for pull-up and pull-down networks. So we have to study other techniques which are which can be used for designing our circuits. In this session, we have to study a couple of techniques. One is our pseudo nMOS circuits and the other one is our tri-state circuits. Let's start from the pseudo nMOS circuits. Before the CMOS technology was matured, single MOS polarity circuits were common. Like they only use MOS like PMOS and nMOS in pull-up and pull-down networks and to design the whole logic. But after the design was matured, the technique was matured, there were different options available where we can design these circuits. The first option was this pseudo nMOS technique. In this pseudo nMOS technique, a single PMOS is added to a complete pull-up network. Like if you see here in this diagram, only one PMOS circuit is added in this whole pull-up network, and this PMOS is always grounded. We will talk about this later, why this is basically connected to ground. So we can say that this technique or this configuration, this produces a pseudo nMOS logic, and this logic uses lower number of transistors. Like if you compare it with the original diagrams where we have been studying about the pull-up and pull-down networks, you can see that in those techniques 2n CMOS transistors were used, but now we have only n plus 1 transistors. Like you have n transistors here and we have 1 transistor for our PMOS. So the total number of transistors reduced significantly. And initially there were some other networks which have only resistor instead of a PMOS, because if you observe this circuit, the purpose of this circuit is only to pull up this logic, pull up this output load line. So there was an option like we only use a resistor here so that we can pull up the network or continuously pull up this load. In this condition here, if you observe this circuit here, if the pull down network is open, like if you open this pull down network, so there is no direct connection from this ground to this output. So it means that we will have output high voltage, and this output high voltage can be represented by VDD. That VDD is applied on this terminal. So it means the PMOS pulls output high. So this PMOS pulls this output to high voltage. So what will happen when this nMOS, the pull down network, is closed? So the next thing we have to observe is the closing of this pull down network. So if this network is closed, it means this network will try to pull down the output to low voltage. Means the output should be around VOL, it should be a low voltage, output low voltage. So we can say that PMOS is always on. It tries to connect the high voltage to output. nMOS, the pull down network, is closed. It tries to get the output to 0, and that means the output cannot be corrected, the output voltage cannot be an ideal 0 volts, because this PMOS is always pulling the output to high voltage. So this family, the purpose of this family of CMOS design was to reduce the number of transistors, because we have seen that the number of transistors were reduced significantly from 2n to only n plus 1. And this family is complicated, because the relative size of transistors decide numerical value of our VOL, the output low voltage. Because this the ratio of this beta P and the ratio of beta N, this basically decides the output low voltage, or what will be the output low voltage should be. The other condition we have to ensure is VOL must be small enough to be an electronic logic 0. If there is a case where our output low voltage is around 1 volt, that means it doesn't represent a logic 0 level. So what we need to do is we have to ensure that this output must be small enough, less than the threshold voltage or close to 0 volts, so that it can be treated as an electronic 0 level. To understand this, let us consider an example of an inverter. The inverter circuit is shown here. In this circuit, we have the source terminal of our PMOS that is connected to VDD. We have this PMOS gate connected to ground. The input voltage applied at this gate terminal of our nMOS is VDD, because we want this nMOS to be closed all the time. And beta P and beta N represents the transconductance of our PMOS and nMOS, and we have an output low voltage. We are considering that the output voltage is a low voltage because this is connected to ground. The nMOS is closed here. So what we do is we set V in to VDD, we have set this value to VDD so that we can get the VOL here. And mode of operation, we have to observe what will be the mode of operation of these both MOSFETs. Why it is necessary to have to understand the mode of operation? Because we know that if we have different mode of operation, we have different equations for the current flowing through these transistors. For non-saturation region, we have a different equation. We have different equation for our saturation region as well. So it is necessary to observe what will be the mode of operation. So if we consider the PFET, this circuit here, this is in saturation region. Why this is in saturation region? Because it is always conducting. It is always connected to ground, and this will conduct all the way. So this will be in saturation region. What will be the case for NFET? NFET, we say that NFET is in non-saturation region, which can be verified by these expressions. The condition for NFET to be in non-saturation region is VDSN should be less than V saturation. Here the VDSN is VDSN means this drain terminal and the source terminal here. This voltage is VOL minus 0 volts. So we replaced VDSN with VOL minus 0. And we know that the V saturation is equal to VGSN minus VTN. And here in this circuit, VGSN is given by VDD. This is VG and this is VS. So this VGSN is equal to VDD. If we replace the values here, we can observe that VOL obviously is a low voltage than this expression, which is VDD minus VT. So we can say that this expression is satisfied, and the NFET here is in non-saturation region. If we have output voltage which is equal to VOL, the same current flows through PMOS and NMOS. And if the current is same through our PMOS and NMOS terminals, we can equate the current equations for both the MOSFETs. This expression is for non-saturation region. This was our NMOS, which operates in non-saturation region, while this PMOS expression is in saturation region. So we equate these equations and solve for VOL, that is output low voltage, and we will get an expression where we have VDD and VTN, and then we have beta P or beta N. So if we observe this equation, we can conclude here that VOL depends on the ratio, that is beta p by beta n. And if we observe this expression here, this beta p by beta n, we can say that if beta n is greater than beta p, this will lower the output low voltage. Like if this beta n is greater than beta p, it means that this expression will be smaller. If this expression will be smaller, this expression will be higher. And if this expression will be higher, and higher value will be subtracted from this expression, so the overall VOL will be reduced. So if we want to achieve a lower value of VOL, this means we have to pick the MOSFETs where beta n should be greater than beta p. So what conditions we have for this pseudo nMOS? We just derive an expression where we said that the aspect ratio of like W by L of MOSFET should be less than the W by L of nMOS. Obviously, this is required to achieve lower output low voltage. But what will happen is it will give us a larger rise time. Why we have a larger rise time? Because we are increasing the size of we are decreasing the size of our PMOS. So we will get a larger rise time. And what other drawback of this technique is like the static power consumption of the circuit is very high, because when our nMOS is conducting, there is a direct path between VDD and ground, so the current is higher. If the current is higher, obviously the power consumption will be increased. And this is a ratioed logic design, where the ratios of beta n and beta p defines two quantities. One is our output low voltage and the other one is our rise time. Because we have seen that if we change the ratios here, the output low voltage can be increased or decreased depending on the ratio. And similarly, the rise time will also be changed. Either it will be higher or lower. So to understand the dependence of VOL on the ratios, we have to solve an example. In this example, consider we have a pseudo nMOS inverter where VDD is equal to 3.3 volts. We have threshold voltages here, like for this nMOS we have a positive threshold voltage, for a PMOS we have a negative threshold voltage. We have device transconductance Kn and Kp, both are given here. And what we have to do is we have to find the ratios for which VOL is less than VDN. We have given two conditions here. In condition 1, the MOSFET like PMOS has a higher aspect ratio than our nMOS. But in the other condition, the second condition here, PMOS has a lower aspect ratio as compared to nMOS. So we have to find for which case, for case 1 or case 2, the VOL is less than the threshold voltage. Or we can say that in which case the VOL will have a logic 0 level. Let us solve for the first case here. In this first case, we have the PMOS aspect ratio is equal to 6 and nMOS aspect ratio is equal to 3. So if we put all the values here in this expression, like all the value we are given with all the values here, we will get an expression. We will get VOL is equal to 1.58 volts. And this cannot be represented by a logic 0 level, because this is not less than VTN, because it is 1.58 volts, it is a very higher voltage. But if we consider case 2, where our PMOS is lower than our nMOS, when we solve this expression for our VOL, we will get a 0.41 volts. And this expression is very acceptable, as it is below than VTN. So we have to choose the ratio of PMOS is less than ratio of nMOS. So we have to choose this second case. So this example illustrates us that the choice of aspect ratios is critical for our designs. If the aspect ratio is not chosen correctly, then there might be a case where we will not get our logic 0 level. So how we can design different circuits using the CMOS, like pseudo nMOS logic? Consider an example where we have designed a NOR gate. Like we have to use same inverter arrays that we have been designing earlier. Just we have to replace the pull-up network with a PMOS the gate of which is connected to ground. So in this case, there is no scaling required of this beta n here, like this beta n here, because we have only single NFET which is turned on during our worst case solutions. So we don't have to scale this beta n. And for n input, like if we generalize this expression, for n input NOR gate, there will obviously be no scaling of beta n for all NFETs, because all NFETs will be in parallel. Like if you draw n like nMOS is here, like there will be n nMOS connected in parallel here. So we will not be required to solve the expression to basically to scale the beta n values. But what will happen in case of a NAND gate design? Same technique can be used to design our NAND gates, but the question is, we have to scale these beta n's here, because these two beta n's are connected in parallel and both these like nMOSes are active. Then the output will be connected to ground. So in this case, if we have a 2 input NAND gate, the beta will be scaled by a factor of 2. But what happens when we have a n input NAND gate? If we have an n input NAND gate, then there will be a scaling factor of n. So all the n like nMOSes are scaled with a factor of n. For the pseudo nMOS case, we can conclude that the usage of this technique may be limited by a few factors. Couple of them are like layout sizing problems, where the devices where the layout sizing problems are critical. So we cannot use the pseudo nMOS circuits there. And the other problem could be the special switching situations, where we need a special switching, because in this case we have studied that the VOL value can be varied. So this might not be a perfect choice for this case. So we might avoid using the pseudo nMOS circuit in these two special cases. The other type of the circuits are the tri-state circuits. Like, what is the requirement of having a tri-state circuit? There may be a case where we require a circuit which may be driven by an output. So what we need is, like, we don't want to drive all the time. So what will we do then? We want a state when the output which is driving a circuit is disconnected, or it is like isolated from the next circuit. So in that case, we have to isolate that circuit. That is similar to like I/O ports in a microcontroller. When a pin is input, like when we are using a pin as an input, the microcontroller obviously is not driving that pin, because it is only meant for reading the data. So it is isolated from the driving circuits. So the tri-state circuits allow us to produce 3 output states. They are like logic low level, high logic, and then we have a high impedance, which is commonly known as high Z state. High Z state means a high impedance level, and high impedance means an open circuit. So to understand this, consider this a tri-state inverter. In this circuit, if you observe that if we ignore this M1 and M2 here, and if we connect this point to this point here, we can see that this is a common an inverter circuit. a normal inverter circuit. So to make it a tri-state circuit, we just added a couple of like MOSFETs, one PMOS and one nMOS, in between the output, like around this output, the terminal. So and obviously this is connected with the same input, that is known as an enable input. There will be different conditions. When in condition 1, when the enable signal is 0, like for example, if this signal is 0, it means that this circuit is open and this is inverted input. It means that this is 1. If this is 1, it means this output is also 1. If this output is 1 and this if this input is 0 and this input is 1, it means both these MOSFETs are in cutoff region. So if both these MOSFETs are in cutoff region, it means there is no direct connection between this point here and this point here. So this F will be in a Z state, or we can say that this will be in a high Z state or a high impedance state. In other case, like when we have En is equal to 1, this nMOS will be turned on, this will be 0, this PMOS will be turned on as well. And then we will have an inverted output at the output terminal, which is represented by F here. What could be the other benefit of our tri-state circuits? The other benefit is this high Z state circuit can hold like value, they can hold an output value even though there is no hardware connection like exists. For example, this output is connected to a capacitor, and when this like circuit was enabled, when this was conducting in our normal case, this output was charged, and in next phase we disconnected this circuit here, we isolated this terminal here, and the capacitor was charged already. And if this capacitor was charged, it means there is no direct path which can be like used to discharge this capacitor. So this capacitor will hold the charge. And layout, if we want to have a look at the layout of the tri-state circuits, this is very simple. Like this was our inverter circuit here, where we have an input at gate terminal and the outputs could have been collected at this point here, but we have added another gates, like 2 gates here, and the inputs of those gates are enable signals. What will happen here? Like if you observe in normal inverter cases, here we collect the outputs at this point, but now in this case we have isolated the output, like this output here, we isolated the output from the original output of our inverter. So this is a straightforward, a simple inverter tri-state inverter circuit. So this was an introduction to the circuits, the tri-state circuits. We normally design our PMOS like pull-up network and pull-down network. We simply add 2 MOSFETs, one PMOS and one nMOS, like around the output node. This represents our tri-state circuits. So this was it for today's session. We have studied about pseudo nMOS and we have also studied about the tri-state circuits. I will just leave you with a question here, like that is up to you to think how can we design this problem. Like the problem is, how can we create a buffer with this tri-state logic? We have seen an inverter here. Like you have to think about it and you have to design. It's up to you how you can design it. Like you have to design a buffer with tri-state logic. So that's it for today. I will see you next video, inshallah.